We're just going to start today with just a real brief note about the scientific method. I read through your comments on Wednesday, and most of you had the right idea about what the scientific method is. You know, it's a process, it involves a series of steps. Those steps include making observations and asking questions, running experiments, testing hypotheses, and so on. But I do want to kind of highlight, or rather underscore, is that this process is an ongoing one. It's not a sequential one where this has to happen and then this and then this and then this in kind of a linear kind of quality. It's very simple because along the way, we are going to be constantly seeking new information. And so, as we're making observations and thinking of questions and formulating hypotheses, we might end up finding the answer that we're looking for. And when we go back and say, okay, well, how can I modify my question? Can I refine my process to answer a different kind of phenomenon or try to do something that's a little bit different than what I was looking at before? And when I get into experimental case, sometimes my experimentation leads me in the direction that I was supposed to go. There's an existing theory out there. It tells me that this should happen. I design an experiment, and sure enough, that happens. That's what going around with me again. Sometimes I do an experiment and I'm supposed to get some kind of result, and I end up getting something different than what I was expecting. And makes me stop and think. Did I do the experiment right? Are my data reliable? Are they valid? Did I make a mistake somewhere, or am I on to something new? And so I go back. Did I look at my data again? I refine my processes. I maybe change the experiment a little bit to account for this kind of error or that kind of error. And I get back to the drawing board and I try it all again. Over time, the scientific method can lead to the development of theories. Theories are generalized kinds of explanations that can predict what is going to happen in a certain situation and to kind of spread it out to a more broad kind of interpretation or prediction. One thing I do want to highlight for you, though, this is actually really important. One thing that we can easily confuse are these two terms here. The idea of a theory versus the idea of a law. One of the most commonly held bad ideas of science is that if a theory becomes good enough, eventually it crosses over this barrier here and becomes a law. That's not true. And the reason why it's not true is because theories and laws are not answering the same question. A theory, like a hypothesis, answers the question of why. Ultimately, theories are explanations. They're explanations for why do certain phenomena occur? Why does it take place in this way? Hypothesis is a general starting point for a theory because they're both answering the same question. A hypothesis is answering that question of why did I see what I saw? Trying to put some words to it. A theory takes that idea of a hypothesis, adds some other concepts to it become much more broad and predictable. Law, on the other hand, doesn't answer the question of why, it answers the question of what. And that answer to the question of what usually comes in the form of some sort of mathematical relationship, equation, some kind of corollary, things that are not really testable. Anyone here familiar with Coulomb's law? Coulomb's law, we'll talk about a little bit. Talking about attraction, particles. So it's basically it's the explanation for how much force attraction you can particles. And you can quantify that relationship based upon what the charge. And how far apart particles they are, that's a law. That is an explanation that is not out of what is the quantity of charge? How far apart are they from each other? The equation itself answers the question of what? What is the amount of energy? What is the amount of force of attraction? Because it's not a matter of debate whether a positive ion or a negative ion attracts each other. They do. The law merely states how to quantify that attraction. I can't test that. Nor can I test gravitation. Gravity exists, period. Gravity exists. We can quantify it. We can use mathematical equations to talk about the force of gravity that exists between two objects. But we really can't test whether gravity exists or not. So that's a really important distinction that we need to make in the framework of the scientific method, is that the ultimate goal of the scientific method is to create better theories, better models that do a better job of putting the world out. Development of laws really only come about as a way of trying to quantify not so much why they exist. So we're going to move on into a short discussion of units. And I'm not gonna highlight everything because again, based on your feedback, this wasn't what we really had any issues with. In terms of what the proper units are for things. I am going to touch on a little bit the idea of temperatures and temperature scales, just because there are some important distinctions to be made there. And a couple of things that I do want to point out. First of all, I want to point out that the most common scales that we have, the Celsius scale, which the rest of the world uses, and the Fahrenheit scale, the scale that we use here in the United States, those two scales are pretty good at looking at things from the context of water, but kind of lousy in any other kind of application. Now, the reason why they are good at looking at things through the context of water, why we use them in weather forecasting, why we use them for doing things like, setting temperatures on our stove or measuring how hot something is when we're cooking on it, is because we live in a world that is, water dominated. Now, these two scales are called relative scales. And they are based on definitions of the freezing point and boiling point of water. So the Fahrenheit scale defines the freezing point of water at Fahrenheit and the boiling point at 212. The Celsius scale using factors 10, 50 and 100, which is also why it is the more popular scale internationally, since most of the world uses the metric system, and the metric system is based on phases of 10 as well. The problem with this scale is that the numbers don't really have a whole lot of meaning outside of, freezing, water freezes at 0 and water boils at 100. Aside from that, you really don't have a whole lot of context. I can't go outside on a 20-degree day, 20-degree Fahrenheit, and say, boy, it's really warm out here. It's twice as warm as it was than yesterday when it was only 10 degrees. I can't make good comparisons on these scales in that kind of way. The difference between 10 Fahrenheit and 20 Fahrenheit isn't really all that great. The difference between 10 Celsius and 20 Celsius isn't all that great either. And part of the reason why that relationship doesn't work is because of the way that these scales are being defined. There's not a real true good comparison that I can use. But on the Kelvin scale, there is. The Kelvin scale sets its only defined value as the last value. 0 degrees Kelvin is something called absolute zero. At absolute zero, all motion stops. And since temperature is a direct analog for molecular motion, when I say that absolute zero is the 0 point of that motion scale, what that means is that everything else can be measured directly as it relates to that 0 point. So if I compare 100 Kelvin versus 200 Kelvin, I'll notice that the molecules at 200 Kelvin are moving quite fast. I can't do that with either of these scales because the definition point isn't based on molecular motion, it's based on phase change. And so because this is based on an absolute 0 point, the Kelvin scale is referred to as an absolute scale. And because of that direct relationship between the scale itself and molecular motion, anytime we do any kind of calculation, any kind of relationship between temperature and energy, we're going to end up using the Kelvin scale as a result. Now, luckily for us, the Celsius scale and the Kelvin scale seem to be lined up. There's 100-degree difference between boiling and freezing on the Celsius scale. There's a 100-degree difference between boiling and freezing on the Kelvin scale. Basically, the Kelvin scale and the Celsius scale jumped up by a 273 degrees. Otherwise, a 1 degree difference means exactly the same on both. And so for that reason, we as scientists are going to do pretty much all of our measuring on the Celsius scale. Because it's very easy to convert that to an absolute when I need to. Now, the way I can go about doing that is with these equations here. So if I want to go between Celsius and Kelvin, and I would get Kelvin. Now to go between Fahrenheit and Celsius, it's a little bit trickier. But I'm gonna offer you alternatives here to these equations because I think it's a little bit easier to work with decimal numbers rather than fractional numbers. And so turning the 9/5 into its natural decimal value, 9/5 is 1.8. So Fahrenheit is 1.8 times degrees Celsius plus 32. If I manipulate this equation algebraically, I get Fahrenheit minus 32 divided by 1.8, and that would give me degrees Celsius. So instead of taking Fahrenheit and multiplying it by 0.55555, which is the fractional of the decimal equivalent of 5/9. Take the Fahrenheit, subtract 32, and then I divide that total by 1.8. Another thing as far as units go, now I made this change in the annotated PowerPoint slides. I'm going to ask you to make it here as well. Some of these prefixes, some of these base units are incorrect. That's on me. I did kind of a sloppy job of proofreading the publisher slides before I posted them. So the kilo here, it's a lowercase k. In fact, all of these here are lowercase values, lowercase b, lowercase c, lowercase m. Lowercase u or micro is also shown with a Greek letter M instead of U. And the other mistake on here is that this 2% is actually a -2. Like I said, those have been fixed on the annotated PowerPoint slides that are in Blackboard, but I didn't get a chance to fix them on here before we had class. So I have made those small changes in your notes. So for the most part, this is the metric scale. The metric scale actually goes well above and well below this part that we're highlighting here. But these are kind of the highlights, the ones that we encounter the most often. And even among these, we could probably string it down to somewhere in between this mega and micro. You know, up to 1 million times the base unit and 1/1,000,000th of the base unit. Nanoscale, picoscale, we see those a little bit when we start talking about wavelengths of light and what things look like on the scale of the atom and the electron. But beyond that discussion, we don't see those two prefixes very often. Mega and giga and tera tend to follow us more in computer sciences than anywhere else when we're talking about storage and capacity, RAM, hard drive, those kinds of things. We will see mega and giga a little bit in our third module when we talk about light and frequencies of light, which tend to be in the mega and giga range. But aside from those applications, we're really going to see more kilo than anything else. Another important thing to pull out of this is that these exponentials refer to the relationship between the base unit and that prefix. So what I mean by that is 10 to the third, there are 10 to the third, 1,000 base units in a unit. So there are 1,000 meters in a kilometer. there are 1,000,000, 10 to the 6, meters in a megameter. And on the flip side, each decimeter is 1/10 of a base meter of a meter. Each centimeter is 1/100th of a meter. So when I'm doing my conversion and I'm using these values, I need to understand that these values go on the base unit when I use them in the conversion, not on whatever the converted unit is. So just as a quick reference here, if I am converting centimeters to meters, and I know, okay, I've got centimeters in the numerator of this fraction, so I want it in the denominator of this one, so they cancel. When I'm trying to figure out, when I'm trying to lay it out here, if I'm using these values, this 10 to the negative second goes on the meter, and 1 goes with the centimeter. 1 centimeter is 10 to the negative second meters. Now, you might know this conversion also as there are 100 centimeters in a meter. And that's basically the same thing, just flipped around. There's 1/100th of a meter in every centimeter, just like there are 100 centimeters in every meter. So if you know the conversions off the top of your head, perfectly fine, perfectly valid, just rattle those off the way that you know them. If you're going to use a table like this, just make sure that you understand what the table means. So all of these numbers here are references to that center unit, that base unit. So with that in mind, we're going to do a question here, but we're going to do this together. And the reason I want to do it together is because I want to highlight a couple of things. First of all, I want to highlight the technique of conversion, which we can then use to start working on this third assignment. I also want to take this as an opportunity to talk a little bit about scientific notation, because I know that was one of the concepts that we had a little bit of issue with on last night's assignment. So the way to solve this problem, is we need to convert all of these into the same unit. These are all derivatives of meters. Let's convert them all to meters so that we can compare them directly. So the first one's already done here. We already have it in a meter. We're good. For the second one, we need to convert millimeters into meters. And so, again, the way that we set this up is through a unit conversion. In a unit conversion, we are basically multiplying a series of fractions by each other. And so, in terms of fractions, we're looking at, we've got millimeters in the numerator here, so we need to put it in the denominator here. Meters up top, the millimeters will cancel. What numbers go in here? Well, this is where we have to call on our know-how. So we either need to know that there are 1,000 millimeters in a meter, or if we go back to that previous table, we would find that there are 10 to the negative third meters in every millimeter. And if I multiply those two numbers together, 321 times 1 to the 10 to the negative third, I would get 0.321 meters. So right now, all we know is that B is larger than A. Haven't gone further than that though. For the next one, we need to convert centimeters into meters as well. So same process, centimeters in the denominator, meters in the numerator, centimeters cancel. Using just our know-how here, I know that every meter has 100 centimeters in it. So dividing 321 by 100, I would get 3.21 meters. For this last one, 3,210 nanometers. I'm converting nanometers this time into meters. And so I've got to consult the chart on this one. Chart says 10 to the negative 9th. So 10 to the negative 9th meters for every nanometer. So if I take 3,210 times 10 to the negative 9th, I get 0.0000321. So we now know the answer to the question is C. C is the largest of the four quantities. 3.21 is larger than all the others. Let's talk about some of the side questions. So first of all, why is I want to use the X and zero when I do this conversion to nanometers or to meters rather? Because it's not significant. So going back to the figures, zeros are kind of the tricky ones. We know every other digit is significant, no matter whether or not it's zero. So zeros that start in are insignificant. They don't gain significance until you get a number that isn't significant. And zeros that anyone are not significant unless there's a decimal point put in there somewhere. Since there's no decimal point there, that zero must not be significant, which means that that number, 3,210, only has 3 significant figures. And so when I convert it, I expect to only have 3 significant figures there as well. That's the first thing that we can look into. Second thing that we can look into is, well, how do we do scientific notation? And so to answer that question, let's talk a little bit about scientific notation. What we need to understand about scientific notation is that it all follows a particular form and format. And that particular form and format is this. We have some number, and it's going to always go number, decimal place, number, 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 for however many numbers we need to get to the correct number of significant figures. Scientific notation always shows us the correct number of significant figures, but it always follows this format: number, decimal point, and then however many other numbers are necessary. So if I only need 1 significant digit, I just start with the number. If I need 2, it's number, decimal point, second number. If I need 5, then I would have 4 digits after the decimal point. How I get to this and how I determine what this value of the exponent is based upon what I have here. And so when I look at what I had in my original, I need to figure out how do I move the decimal to get to this format, and based upon which direction I move, and how many places I moved it, that's going to tell me what my exponent is. If I move to the left, that means that the integer is going to be positive. If I move to the right, that means that the integer is going to be negative. Now it's just a matter of how many times did I have to use that decimal. So if I come back to my numbers here, so if I come back to these three numbers here, to turn them into scientific notation, I would need to move the decimal point, in this case, one spot over to the right. So the number here is 3.21. The exponent would be -1. Negative because I moved to the right, 1 because I moved it one position. And I would still keep the meters because the unit didn't change here at all. For the second one, 3.21, I've already got it in the correct format. Number, decimal point, other numbers. If I had to put a scientific notation flare on it, how many places did I move the decimal point? 0. So that would be my exponent. In the case of this last one, I have to move it 1, 2, 3, 4, 5, 6 spots to the right. So my exponent there would be -6. So that's as easy as scientific notation really gets. Now, if I have to go the other direction, all that changes is the direction that I move the decimal. Maybe to the left, to the right. I would add zeros or take zeros away as is necessary to use it. Right? Any questions with scientific notation? I have a sticking point yesterday. I wanted to make sure that we were all on the same page. All right, then what I want to get into, we're going to skip over this stuff about precision and accuracy. We didn't seem to really have any problems with that. Let's get into just some actual questions here about sig figs themselves. How many sig figs are in that number right there? Put it in top half. Last couple seconds, try to get in what you can. Okay, we're a little bit split on it. Don't worry, they were this morning as well. But the correct answer, as Charles said, was 5. Now, how do we get that? So let's look at the number here. Remember, zeros that start with the number don't count. So Even though there are really places starting this number, they don't have. Zeros don't start counting until we hit something that isn't a zero. So when you start hitting that there, you can start counting. And so, including the 3, there are 5 digits that are after that one. So the correct answer there is 5. That 0 at the end is significant. It is significant. Because it's at the end of a number and we've got a decimal point on it. So it's there to reflect precision. All right, let's try one more. And then we will call it a day here. What about this number? How many significant figures are in this number? Correct answer here is all of them. We're not starting with 0, so we've got even though we have 0 at the end, that's the one in the middle of it. That again is pending precision. All of those digits are significant. And if I count them up, there are 9 of them in total. So most of you we're on the right track there. So, like I said, where we're going on Monday is we're going to get into a more concrete look at unit conversion and dimensional analysis using that factor label cancellation technique to solve more complex kind of conversions. If you understood kind of the basics behind what we were doing when we did those metric conversions, basically all that we're doing on Monday is an extension of that.